Hey folks, today we're going to switch gears a little bit. We're going to talk about light. So there's no math, at least nothing exciting yet. So when we think about light, what do we think of? Clearly you think of the sun. Anything else? Sure, you probably think about a light bulb, right? But my question is, could it be dark? I mean, could you be sitting in a completely dark room, like in a bathroom with no windows, and be midnight, and can there still be light in where you are? Well, let me ask you this. When you're outside, lying in the sun, and you lather yourself up with sunblock, why do you do that? Well, you're protecting yourself from UV rays. If you look at this, it talks about UVA and UVB rays. You're protecting yourself from ultraviolet rays. Can you see ultraviolet light? No, you can't. It's outside the range of our visible spectrum. Our eyes can't pick up ultraviolet light. So ultraviolet light, if we look at a rainbow, we can see red, and you understand Roy G. Biv colors. But over here, there's purple, and you can't see that purple. Similarly, you can't see the infrared that's on that side of the rainbow. So it's there. It's coming out of the sun. You just can't see it. It's invisible to our eyes. There are other kinds of electromagnetic radiation, such as X-rays, which we cannot see. We cannot see microwaves. So if you look above Hidden Valley, you will see these microwave towers. Right? Or you can look on the side of some houses and you see dish network dishes. These are microwave links to transmitters in the case of Dish Network that are up in space. And in the case of Hidden Valley, we're talking to other schools. And you don't see any light coming out of those even at night. You don't see any light when you're looking at a television tower or a radio tower or any of those, or a cell phone tower, except maybe for a red flashing light that's up here, but that's visible light. You don't see any light coming out of these, but they are all transmitting all at the same time. All right? Bottom line is our eyes only see a very small amount of the spectrum, from about 400 nanometers in wavelength to about 700 nanometers in wavelength, and everything else is not visible. So we cannot see X-rays, we cannot see cosmic and gamma rays, but they're there. We can't see infrared, ultraviolet, we can't see microwaves or radio waves. You know, we have FM radio wave signals all around us. Those actually are light. Okay, but we just can't see them. We don't call them light, but they are light. When you look at your microwave and you turn it on, do you see light? Well, actually, yes, you do. Okay, and the reason that you do is over here, there's probably a light bulb that's on when your microwave is on, and that's simply to tell you that your microwave is on. It's a safety device. But if that light burns out, or you go in and you take it out, you will have no way by looking in the microwave to see if it's on or not, because you can't see microwaves. Microwaves are way over here. They are way below the infrared spectrum, so we can't see them at all. Notice down here are FM and AM radio waves. You can't see them. Walk outside. Can you see FM radio waves? I don't think so. All right? So all of these other parts of light are out here, and we only see this very, very small amount of the visible spectrum, which is right there. Okay? So how do we demonstrate that light is actually a wave? Well, polarized sunglasses are designed specifically because light is made of waves. So let's see how they work. Right? When we look at a three-dimensional movie, when we look at a 3D movie, we wear these really funky glasses. Okay? And the really funky glasses are important when we're watching a 3D movie because that's the only way you can see it. So how does a 3D movie work? Well, if you're in the movie theater, you have a you have a projector that's projecting from the back of the theater, and it's projecting all the way up on here to a screen. Okay? And when you do that, the projector has in front of it a filter. And the filter, you'll have one filter that only allows vertical light through. So light is produced in all orientations, but this filter is like a screen, and it only allows the waves that are going vertically to pass through, and they will come down, they will hit the screen, and then they will bounce off the screen, and they are still bouncing off in a vertical orientation. Right? Now over here you have a second projector that's also projecting at the screen, but this one has a horizontal filter, and it only allows light to go through that's going through in a horizontal orientation. So when it comes back at you, and it's coming back at you, bouncing off the screen in a horizontal orientation. So what? Here's where the fun comes in. You're sitting here in the middle, right? And you're watching the movie. Thank you. And you're wearing these funky glasses. And this lens only lets through, it has a screen on it, which you can't see because it's so small, right? But it's all vertical lines, and it only lets through vertical light. And this one over here only lets through horizontal light. So as a result, one eye is only picking up vertical light, and one eye is only picking up horizontal light. Now your eye couldn't care less whether it was horizontal or vertical light, but your eyes now are picking up two different images, which your brain then puts together into a stereoscopic or three-dimensional picture. And that's how 3D movies work. So let's say that I were to take one lens, this lens, and I were to put it on top of that lens. I shouldn't be able to let any light through. Or, alternatively, I take a whole other pair of glasses, and I take this lens, and I orient the glasses this way. And as a result, this lens would now be covered with another one that had the lines that way, and I shouldn't be able to see anything through it. So that would be the concept if I could do that. So let's see, I'm going to go in and put on a video, I hope, that will demonstrate that to you.
Hi folks, here we have some polarized sunglasses. Actually, they're for watching 3D movies. They're from Walt Disney World. So we're going to see how these work and demonstrate to you the concept of light as a wave, and demonstrate to you beyond the shadow of a doubt that light is a wave. So here I have one pair of polarized sunglasses, and here I have another pair of polarized sunglasses. And you should be able to see that you can see the light through them. I'm specifically looking at the left-hand lens here, right, trying to look at that light. And notice that as I turn these lenses so that they're 90 degrees to each other, notice what happens as you're looking for the light. The light disappears. All right? So when these things hit 90 degrees, you can't see through them. Okay? So we're going to talk about exactly why that happens in the podcast.
Wasn't that a cool video? Now you can see how the lenses actually prevent light from getting through. The most important thing with this is not just that it's cool, but that you realize that this demonstrates to you beyond any doubt that light is a wave. Because if light wasn't a wave, then these little screeny things wouldn't work. Alright, so as we look at wavelength, frequency, and energy, you need to make sure that you understand something. And these are things that I hope you don't have to memorize. I hope you can logically reason through this. Is that if I have something that has a low frequency, it has a long wavelength. Okay? So a low frequency would mean it hits you infrequently. High frequency means it hits you very frequently. Now, it's not hitting you any harder, but it's sure doing more damage, right? And it's sure more irritating. Okay? So the higher the frequency, the more damage that's going to be done. The lower the frequency, the less damage. So now let's look at what colors we have. Over here on the left we have a red color. Well, that's hitting us very infrequently. But the blue color, or the purple color on the right, that's hitting us very frequently. So that should do more damage. Now, doesn't that make sense? Because when we use sunblock, we're trying to block the ultraviolet rays, which are out here. So we're trying to block the ultraviolet rays. So they are a higher frequency than our red light, which is infrared, which is a lower frequency. Right? So the higher frequency light has more energy, and the wavelength is much shorter. The waves are closer together. Right? So you should know that. You shouldn't have to memorize the fact that red has a longer wavelength or a lower frequency, whereas violet has the shorter wavelength and the higher frequency. Okay? Because your violet light does more damage. All right. So let's look at some wave characteristics. We have a bunch of characteristics we need to understand. There are 4 of them specifically, and the first one is amplitude. And amplitude talks about how bright, how high the wave is, and hence how bright in the case of light that would be, or in the case of sound, how loud it would be. Right? So this is amplitude. It goes from the origin of the wave to the high point, or you could say from the origin to the low point. It really doesn't matter. Okay? So it's origin to crest, brightness, intensity. Okay? For sound, it's loud versus soft. Now, I'm not changing the pitch. I'm just changing loud versus soft. So the next thing we can look at is wavelength. Wavelength goes typically from crest to crest. Okay. Now, we could do it from the bottom to the bottom. That's cool. We could do that. Now, your visible light is typically 400 to 750 nanometers in light. Nanometers are very, very, very small. Okay. Now, how about frequency? Well, the green one that we have, which I'm going to circle the tops of the green ones, right? The green ones are very frequent. Whereas the yellow one, look at the yellow one. The yellow one is going from here all the way up to there, down to there. So the yellow one is not as frequent. Okay. So when we look at waves, the frequency tells excuse me, how fast a wave oscillates up and down. And we measure that in sometimes per second or divided by second. Sometimes we call it cycles per second or hertz. This is the one that makes more sense to me when I call it this. How many times is the wave cycling up and down per second? Now we call it hertz. Now that's a term you're familiar with because 94.9 Star Country is at 94.9 million or megahertz. All right. So Star Country broadcasts at 94.9 million hertz. That's times 10 to the 6th cycles per second. But light, the visible light that we can see, goes at 10 to the 14th cycles per second. So more than twice as many cycles in every second. In fact, tens of thousands. What is that? Let's see, 6, 7 million, over a million times faster, right? Million times more frequent. Okay. So for sound, a higher frequency increases the pitch. Okay, a higher note, like if you're playing piano, a higher note on the scale. It has absolutely no impact on volume. For light, it simply moves towards the violet side. Higher frequency means it's more damaging. Lower frequency would create a lower note for sound. Again, it has no impact on volume, and it moves towards the red end. All right, what happens when I combine them? Right. Well, look up here, and you'll notice that I have the green and the yellow almost at their peak at the same time. Well, when that happens, we combine the two peaks, and you get something that's much higher. Now, when I get two things, when I get two things that are low together, like here, you're going to lower that one. So again, two things that are high together are going to go up and get higher. Two things that are close to low together, which is right there, those two, are going to get lower, much lower. If they're both in the middle, they don't matter. And if you have something where you have a high of one and a low of another, they're also going to cancel each other out. All right. So what you get is a very uneven mess. And if you think about what happens behind a boat, if you've ever seen two boats that are traveling along and they put out waves behind them like that, here's the boat up here. All right. And you've got another boat over here, and it's going that they're both going this way. All right. And these waves start to overlap. Right. And if you happen to get a tube out here, you're in trouble because those waves are really, really huge. Well, that's exactly what's going on. So when you add two waves together, you get a picture kind of like this, where you get some very high highs and you get some very low lows, and it makes a mess. Okay. So let's talk about light waves. Light waves are very unique. Light waves are unique in one way, and that is that their speed is always constant. So when you think of waves on the ocean, speed is not constant. But light waves, they always travel at the same speed of 3 times 10 to the 8th meters per second. Okay? That's a real big number, and if you do the math, you find out that's about 186,000 miles per second, which is multiple times around the Earth, okay, in 1 second. So the light travels very, very, very quickly. So, what does this all have to do with chemistry? Next podcast, right? We'll do that in a few minutes. So, let's summarize this one. Light is much more than visible light. You need to understand that there are X-rays and radio waves and everything way beyond the visible spectrum, and they're all around us all the time. You need to understand which light is less and more damaging. More damaging would be something like X-rays. Less damaging would be something like radio waves. Light does travel in waves. You need to understand the difference between frequency, wavelength, amplitude, and speed. You need to know that higher frequency is much more damaging. Lower frequency is less damaging. And the higher frequency light is going to be stuff like ultraviolet light and X-rays. And lower frequency light is going to be stuff like infrared or radio waves. All right? That's it, gratefully. If you have questions, come ask me. I'll see you in class. Have a good day. Bye.